So we'll start with the transistors, and transistor, as we know, is actually the topic broadly that we have in our third unit. Okay, and for the basics, I guess the first thing is we should actually know the definition of transistor. That's important. Okay, and I think we already know that if we have two PN junctions, okay, so if you consider this would be one PN junction here, okay, and the other PN junction will be this, okay. So this will be the other PN junction, the second PN junction. So you have got two PN junctions, and what happens is if you have two different types of semiconductors, let's say the N type, then you will have a P type in between. If you have P type on both sides, you will have an N type between. Okay, and that's how we actually have a PNP transistor or an NPN transistor. Okay. So in general, we have got two types of transistors, PNP and NPN. Now the question is, this is also very basic, that where do we exactly get the name transistors? Okay, so the word trans usually comes from the word transfer. Okay, and ISTORS actually comes from the word resistor. So if you just remember this, okay, what happens usually is that the input is more or less forward biased. Okay, so you have got three sections here. Okay, we are just going to discuss about those three sections. So in these three sections, what we have here is the input, which is actually forward biased. Okay, so you have negative here, and then you have got the p-type connected to the positive terminal, so that is nothing but forward bias, right? The output terminal is basically in the reverse bias condition, okay, and that is usually how the transistors are designed, okay. And then you have got N connected to the positive terminal, and the base is connected to the negative terminal here. So this is the configuration for NPN transistor. If you want to do a configuration for PNP transistor, accordingly we will forward bias or reverse bias the input and the output terminal, right? Also, we know that the output terminal, the biasing has to be more intense. Okay, we have to give a more voltage compared to the input voltage, and that's why I have drawn more cells compared to the input terminal. Okay, so these are certain instances or certain important points regarding transistors that we should all be aware of. Okay, so that's important. So before I go into the symbol and all, let's just start with this. It was actually invented in the year 1948, okay, and it was invented by J. Burdeen and W. H. Brattain, okay. So they actually invented it in the Bell Labs, okay. That's actually Bell Telephone Labs, okay, and it was in USA. So this invention of transistor has done a lot, has brought about a kind of revolution in 1960s and 70s, because if you remember something which we call as vacuum tubes, okay, and that was actually the device that was used before the transistors were discovered and actually featured in the modern electronics that we use. But in those traditional electronic equipment, we actually had the vacuum tubes, okay. So what happens is that if we have a signal and let's say I want to amplify that signal, okay, what we do usually is we actually use a transistor. But then if we use a vacuum tube for the same purpose, it actually needs a lot of power, okay, it needs a lot of input voltage, and at the same time it also generates a lot of heat. So nowadays, any device, you usually don't see a vacuum tube being used. Okay, so that's important, and that is exactly how our transistor is a good replacement for a vacuum tube. Okay, so in general, I think the symbol is also known to all of us. Okay, it's very simple. We basically have this. Okay, and then on one side we actually have the base. Okay, and then on the other side we have got the collector, okay, and then the third side we will actually have the emitter. So this is your base, okay, that's collector and that's emitter, okay, and that's important. So let's just revise this. So this is base, okay, and then this is your, let's say, emitter. It's not that you cannot change the orientation, you can, depends on how you're drawing the diagram, but then leveling it is more important. And then we have basically got the collector. So you basically have these three sections, okay, and why we call them as emitter, base, and collector, it depends on their basic purpose, okay. So the base is actually input, is common to both input and output in this particular circuit, okay. So this circuit is something which we call as the CB configuration, so it is common base configuration, okay. So in a similar way, I can have a transistor where the emitter might be common to both input and output, or the collector might be common to both input and output, and so on. Okay. So if you look into this, we basically have the base here. Okay. So okay, let me just delete this. Probably take up this. Okay. So this is your base, right? And then this is your collector, right? And base is in the center. This is your base. This is your collector. Okay. And on this side, you actually have the emitter. But then it's very difficult to just draw this NPN transistor in such boxes. It becomes a bit complicated, right? So in general, the emitter gets its name because it emits the electron, passes through the base, and the collector will collect the electron. Okay. But before that, I think I should explain the symbol to you and how the notations are usually done. So I'm just considering a PNP transistor. So if you just consider, sorry, let's say an NPN transistor. So NPN means your base is positive. Okay. So this is P, and then this is N, and then this is N. Okay. So whenever I say there is electron, it will always flow from a region of higher potential. Positive is considered to be a region of higher potential to a region of lower potential, right? So the flow of electron is in this particular direction in general, correct? So you see base is P and the emitter is N. And if you want to denote whether our transistor is PNP or NPN, we have to use an arrow in the emitter junction. So I will take a emitter junction and I will put an arrow here. Now this arrow is pointing from the base towards the emitter. That means it is going from P. So the base is actually sandwiched between two similar semiconductors. So if it is P and P, okay, you will be having the arrow in the opposite direction. Okay. So this basic convention remains the same. There is no change as such. Okay. Also, one more thing that sometimes we actually get a bit confused, okay, very important. What we basically call it as the conventional current, okay, conventional current, okay, conventional current, okay. So, current will always flow in a direction opposite to the flow of electrons. This is the basic definition that we know, okay. So, uh, in this particular explanation of whatever we are going to study, we are just going to concentrate on the fact that what is the direction of flow of electrons, okay. So we'll just take that convention, okay, but that anyway we're going to go into that later. Okay, so please keep a note of these three important parts here. Okay, so you've got the emitter base collector, this is the symbol, and how we exactly put the arrow signs, I think it is also very obvious, and I think it's clear to you, right? So this is important. So I guess I can just write down few points on the base, emitter and collector. Okay, so probably we can start with the emitter. So let's start with what we actually know about the emitter. Okay, so emitter is always. I think we should write down this. Emitter is always forward biased. Okay, I'll just write down FB, forward bias. Okay, with respect to base. So if you just take it with respect to base, this will always be forward biased, as we have seen in the diagram. Okay, so these are some important parts of transistors, so that we can actually be very clear about it. Okay, why we actually have that? So that there is a large number of of majority charge carriers. Okay, and that is why they should actually be forward biased. Okay, so I think this is quite obvious. And then we do have the collector. Okay, and probably I'll use the same sentence here. Okay, the collector is always reverse biased with respect to the base. Okay, collector is always, it is reverse biased, right? So it is reverse biased with respect to the base. So whenever you are drawing it, I think it's very important that you do it correctly. Okay, it has got its own application. Okay, so what happens is basically in emitter is you are actually forward biasing it, so you are having the charge actually flowing from the emitter towards the base. Okay, but then when it's collector, the main role of a collector is actually to collect those charges. Okay, and whether the electrons will flow from the emitter to the base or the holes will flow from the emitter to the base will actually depend on whether you have a NPN transistor or a PNP transistor, right? So I think this is quite obvious to all of us. Let's just go back to the diagram here. So what we have here usually is, let's say we have got some electrons here, right? So maybe I can just take this, and let's say uh, so I have the electrons here, right? I have the electrons here, and I know that this is forward bias, right? So I am applying, and then this is the direction of flow of electrons, and this is what is happening in this case. Okay, so that is actually the current that is flowing, the conventional current that is flowing. Okay, and that is in the direction of the flow of electrons. Okay. On the other hand, if you are basically having a PNP transistor, let me just quickly draw this. Okay, so we can just draw this. So this is P, this is N, this is P, and this particular case, it's not the electrons that are flowing, but in fact the holes that are flowing. Okay, so hole is flowing in this direction. That means effectively the electron is flowing in the other direction. So here, if you see that the flow of current in this direction, and this particular case, if we connect it with the circuit, the flow of current will be in this particular direction. Okay, so this is a very important basic that all of us should be clear about. Okay, so this is important. Okay, let's just go back to that page again. Okay, so that I just repeated this because I think this is important. All of us should know it. Okay. So collector. Okay, we're talking about collectors here. Okay. So collector is always in reverse bias with respect to the emitter. Okay. There are some more points and same, but let's just write down this base. So it's the middle section and it is very thin. Okay, so it's the middle section and very thin. Okay, this is important, and it will actually be the junction between the emitter and the collector. Okay, so we already know they're very thin, and the junction between the emitter and collector. So the basic here is actually now how does the PN junction work. Okay, if we know the working of a PN junction, two PN junctions connect with one after the other, we can also understand how does that work. Okay, so basically what happens with the size, okay, important. So emitter, if you consider, is mm, is thinner than the collector because we need to generate more charge carriers there. Okay, so emitter is basically thinner than the collector. Okay, base is thin, in fact it's the thinnest among all three. Okay, so I can just write down this, thinnest among all three. Okay, and collector is always reverse with reverse bias with respect to base and larger in size. So the question is, if I actually draw it, why do I draw it in the other way that we are not actually looking into the size? Well, that's actually not the thing is we are just following a convention where we actually really don't consider the size. Okay, but if you look into a practical device, you will see that the emitter may be this much size. Okay, the base is thin, and the collector will be larger in size. Okay, so the emitter will be basically this much. Let's say it will generate the charge carriers, and then this is the base, which is actually the thinnest part of this transistor, and then this is the base, and then this is the collector. So the collector is having a greater width. Okay, so a very fundamental idea is like why the collector is having a greater width. Okay, so what happens is the first task of a collector is collect electrons. So the chances are that it can collect more electrons coming out of the emitter, okay, and actually generate a better output. So because the main aim is to amplify a signal, that was the fundamental application of transistor, to amplify a signal. That's the first part. And second part is as the electron keeps on crossing the base, it will actually also generate heat. Okay, so that heat needs to be dissipated. So if you have a very small portion, the chances are that the transistor will get damaged if more and more electron flows to the collector. Okay, so this is not something which I'm going to write, but I think you have to understand this fundamental idea. Collector usually also helps to dissipate the heat. So if there is a larger portion where the electrons can flow, the heat gets dissipated and we have a better transistor with longer life. Okay, so that's important. Okay, so then this is important. And what about doping now? Okay, so doping is again a very important part because you are talking about a PNP and an NPN transistor. How strongly are we actually doping them? Okay, so emitter, we actually need to have more and more charge carriers. So we can say that emitter is heavily doped. So I'm just writing down all the points here so that you are not confused here. Okay. So why? Because you want to inject a large number of charge carriers into the collector, and so they are heavily doped. Okay. So I'm not writing down all the points. Please, you have to remember some of these points. This is very important. Okay. So the base is very lightly doped. Okay. Since it's the thinnest, it doesn't have that much scope of doping also. So the base is lightly doped. Okay. Now then, what about the collector? The collector is actually moderately doped or intermediately doped, okay? Because collector also has a role there. Collector is, you can say, moderately doped. So these are the important points that you should remember about the base, emitter, and collector. Okay, so this is the actual design, you can say, where the collector appears to be larger compared to emitter, but then practically we usually draw everything of the same size. Okay, so that is perfectly fine. And we always have this part as forward biased and this part is reverse biased, and that is very important. Okay, so if there is a question on how does a transistor work, maybe I can just give you a few points here, but then the working, whatever I said is almost explained there. Okay, so working. So let's just talk a bit about the working. Okay, what are the points that you should remember when you actually write down the working of a transistor? Okay. Before that, I think one more point I can give you here. Okay. Just go back to the previous slide. Okay, and I'll just give you a note here. I think this is important. So what happens if there is no emitter current? Okay, if the emitter current is zero, do we get any kind of collector current? Okay, so what happens here is if emitter current is zero, okay, zero, then collector current is nearly zero. So question is, if I say nearly zero, does it mean that it's not exactly zero? The answer is actually yes. It might not be exactly zero because there are some minority charge carriers also. So even if you remove the entire emitter base junction, the collector base will actually give some current, okay, and that is actually called you can say it as the dark current or the leakage current. Okay, so if the emitter current is zero, then the collector current is nearly zero. This is the word nearly is very important. And in case if let's say emitter current is, let's say, 1 milliamperes, it cannot be that high, then collector current is nearly 1 milliampere. Okay, so this is important. So let's just go into more detail and try to understand why do I say that it is nearly zero and not exactly zero. Okay, so what happens here is, okay, so I've already written a page. Let's delete this. Okay, so we have, let's just talk about the working now. Okay, and some few points about working, which is actually very important. Okay. Okay, so the first thing is basically I've already shown you the for diagram. Okay, so the first thing is forward bias allows the electrons. Okay, forward bias allows the electrons to flow. Okay, flow in. I'll just take one example. Let me take this N-type semiconductor in N-type. Okay, N-type towards the base. Okay, let's say it's towards the, that's one point, very important. Okay, and then number two, this actually will constitute the emitter current. Okay, let me just do this. Constitutes the emitter current. So you have a emitter current flowing. So you have the forward bias connection, and then you are actually having the emitter current actually flowing through this. Okay, so maybe I can just select this diagram rather. Okay, okay. Let me just select this diagram here. Capture part of this. Okay. This. Okay. Add to current page. Okay, add to new page. So I have this figure here. Okay, let's just take this figure. Let me just go back here. Can be paste. Oh, I don't have an option of pasting here. Okay. So maybe I'll just delete this page, just take up a new page altogether. Let me just finish this writing part first. Okay, so this basically constitutes the emitter current. Okay, so this constitutes the emitter current. So this is important. Okay, so this will actually constitute the emitter current. Now once the current starts flowing, okay, you basically have, let's say I'm considering an NPN transistor, you have got the p-type base. Okay, so if I just draw that figure, okay, if I just draw that figure again, I guess I think I should do it once more. It's too hazy. So I'm considering an NPN transistor, okay, and I'm just drawing it. I have the base in between. I won't level everything here. You already know it now. And then let me just take this, take small, take this, take small. So I basically have an NPN transistor here, and then on this side I basically have got the base current. Okay, so this side I have got the base current. Sorry, emitter current, not base current. On the emitter current. Okay, so the emitter current will basically start flowing. Okay. So as these electrons flow through the p-type base, they basically tend to combine with the holes. So you have the electrons here and you have some holes here. Okay, it's a p-type semiconductor. Of course, it is lightly doped, but there will be some holes which are actually present. Okay, so there are chances that some of these electrons will actually combine with only some of these holes. Okay, so what we can write down this is, let me just write down one. Okay, let me just write out it in normal sentences. I think this will be more easy for all of you. Okay, so the electrons will combine with few holes of the base, but max electrons will reach the collector. This is important. So as the base is very lightly doped, okay, and it's very thin, therefore we have only few electrons which will actually combine with the holes, okay, in the base. So the electrons will combine with few holes of the base. Let me just give you a normal value here. Okay, about 5%. How much you last? So let's say about 5%. Okay, so that's not going to affect much of the current, but then most of them electrons will actually reach the collector. So the remaining 95% electrons will actually reach the collector. Okay? That's important, and this will actually constitute the collector current. So which constitutes the collector current. Collector current. If you ask me to just write down equation here, okay, what I can do here is probably I can just write down here. Okay, IE emitter current is equal to the base current plus the collector current. And I know, I hope you understand that why there is a base current and a collector current, because some of these electrons will actually constitute a combination with the electrons or the holes which is present in the base. So this will be actually 95%. So now you understand the fact that I've given in the previous slide, that what happens usually is that if the emitter current is zero, the collector current is almost zero. Okay, I'll come to that later. But then if the emitter current is, let's say, 1 milliampere, okay, you will have the collector current will be almost equal to 1 milliampere because it is 95%. So you're going to have almost equivalent to the emitter current, which is 1 milliampere. Okay. So what happens usually here is that you have the electrons coming from this side to this side. Until and unless it comes and flows along this direction, you are not going to get any current in the circuit. So you want to grab more electron to come from this end to this end, and as a result of which this is actually quite high. Okay, so if you just consider the uh, collector base voltage, okay, and this is, let's say, the emitter base voltage, we do have the emitter base voltage less than the collector base voltage, because if it is a positive terminal and you have even electrons coming here, because of this high potential on this end, the electrons will easily flow in this direction. Okay, so this will actually constitute the collector current. Sorry, not the base current, the collector current. Okay, so this is important. And then you have the base current flowing across this direction. So if you consider the base current, you basically have it here, because some of the electron was actually stopped by the base, so that electron will actually take this path and flow along this direction. Okay, so this is exactly how it works. Okay, and then if you just look into this diagram conventionally, and if you want to actually look into the let's say the direction of flow of current, I think I can draw this here. Take this, take this, take this. Base current will flow in this particular circuit, and the collector current will take up this path. But then most of these currents will actually flow around this direction. Okay, so that's important. So it depends on whether you are considering an NPN transistor or a PNP transistor. Okay, so what I'm doing here is I'm considering an N, a P, and an N transistor. So I've explained you NPN transistor, and then I think PNP transistor is analogous to it. Okay, and then it's your task to actually check the PNP transistor and try to understand how does that work. Okay, so you know transistor Xn plays a very important role in order to understand the amplification system. Okay, the amplification process, that is very important. Okay, and then I think the symbols are very much clear to you and should not be very confused. Okay, and then as far as application is concerned, transistors are mostly used as amplifiers. Okay, so we will actually have a session where you all would be presenting, and then I'd like to keep this topic for that particular presentation, where some of you would at least explain how does the transistor actually acts as amplifier. Okay, so you know they can actually look into that circuit, check your old notes and all, and then you'll understand how does it work as an amplifier. But anyway, we'll just continue with some more basics. So one is I think important is transistors connection. How are they connected? Okay, and then this is something which I already told, but then anyway we can just do a very quick revision on this. Okay, so what happens is you basically have an input signal, and then you are actually getting an output signal from there. Okay, and based on that you have got some important configurations that are important. Okay, so I'm not going to draw each of them. I think this will be a bit more time taking. Okay, and I don't think it needs to be explained to you all. So one we have is the common base connection. Okay, and number two we have got the common collector connection. All of them has got their significant applications. Okay, but common base connection is something which is more exploited when we look into a transistor acting as an amplifier. We can also use the common base connection. Okay, so common base connection, common collector connection, and common emitter connection, and depending on that you are actually making it. Okay, so what do we mean by common? That means the base is common to both input and output. In this case the collector is common to both input and output, and in this case the emitter is common to both input and output. Okay, but then I'm just going to consider the common base connection and trying to explain some finer points that we need to know. Okay, so let me just keep this here, and let's just try to explain common base. So common base connection is important. Okay, let's try to understand it. Okay, so in common base connection what happens is I am not going to write this, but base is common to both input and output. That what happens is that you are going to give an input signal and you are going to get an output signal, okay, out of it. And whenever you are actually making the circuit, you have to also connect some resistors and so on, so that you are actually going to get a desirable result, right? It's something like an amplification signal, because even if you are applying an input voltage, you're going to get an output voltage. Will that voltage ratio be same or different is something which you're going to look into now. Okay, so a very important term that we have in this is, okay, current amplification factor. Current amplification factor. So I'm just considering the common base configuration, and let's try to understand what exactly do we mean by current amplification factor. Okay, so how much current is amplified with respect to the input current. So I've given some kind of input current, and then how much current I'm getting at the output is basically nothing but the current amplification factor. Okay, so it is mm, the ratio, and this will actually help us to solve some numerical problem of output current to input current, right? So this is the current amplification factor, which is important. And what happens is that if you are considering a common base configuration, okay, in CB config, okay, IE is the input current, and IC is basically the output current, right? IC is the output current, is the output current. So this is good. I think this is clear. And what happens here is that I think, yeah, okay, I've not written the symbol here. So current amplification factor is usually denoted by alpha. Okay. So if I just write down alpha for a common base configuration, okay, let me just write down CB here. But in general, I just write down alpha. You all can also write down alpha. You don't really need to specifically mention CB, because as soon as I see the right hand side, okay, or the left hand side, sorry, I know that what current I'm talking about. So we are talking about emitter current divided by the collector current. Okay, collector current. So this is important. So once we know this, we can actually find out what is the change. Okay, so this will basically give you the change in the collector current with respect to the emitter current. Okay, and this is actually done when the base voltage, okay, is basically constant. Okay, so this is important to know that we are not going to vary the voltage, because if we vary the voltage, the amount of emitter current will actually keep on changing. So at a constant base voltage. So base voltage we usually denote it as CB. Okay, so this is actually called the current amplification factor. So it's a very important question for your exam. Okay, and based on this, they do give numerical also, be it your exam or be it your entrance exam and so on. Okay, so what happens is that it is quite clear that the current amplification factor will mostly be less than unity. Okay, you know, if you have the emitter current and 95% of that actually crosses the base, you are going to have this, okay, as a larger value. Okay, and what happens here is, if I just consider this at a common base voltage, okay, you're going to get IE divided by IC. Okay, so this current amplification factor is going to be very close to unity, or might be even less than unity also. That's possible. Okay, so what we do is basically we increase the value, and then you might argue that if the current amplification factor is very close to unity, okay, let me just write down this. This is very close to unity, very close to 1. If this is very close to 1, then whatever is the input current, same is the output current. Then how do I get amplification in the signal? Okay, the answer actually lies in the resistor that you are using. So if you are basically considering a connection, okay, let me just quickly draw the circuit here. Okay, so if you have a base here, and then we have got the emitter, and let me just write it down as a PNP transistor. Okay, and then we can just draw it here. Okay, so this is base is positive, so I'll just keep it forward bias. Okay, and on this end I will just keep it as reverse biased. Okay, so reverse bias, so I'll just take this ये क्या था n था, so I'll just take this to be positive. So this is negative, this is positive, this is negative. Okay, so pardon my drawing, it's not that good till coming in terms with this digital pen. Okay, so what happens is that the current is actually measured across our load resistance. So we have got a load resistance connected across the output. So this is RL. Okay. So the input current might be IE, okay, but the output current will be whatever is the current, and the RL factor is there. So if you just consider this, V is equal to IR, then you can actually find out what is the current in the output. Okay, so this is what is the current amplification factor is all about. But based on this, actually we are just going to do one numerical, and I think this will be more easy for all of us. Okay, so the practical value of alpha in commercial transistor is basically 0.9 to 0.99. Okay, so just write it here. Practical value of alpha, okay, is 0.9 to 0.99. Okay, so this is again important. Alpha लिख लेते हैं यहाँ पे. So next is something which we call as the expression for collector current. So I say that we have got the emitter current. Now I need to check that whether the emitter current is large enough or not. Okay, so collector current. Okay, collector. Just look into the amplification, how exactly it happens. Okay, so you know the whole of emitter current does not reach the collector. Okay, some of them are actually getting lost in the base, because you know a very small portion of it will actually combine with the holes of the base, and as a result of which some of the electrons will actually not reach there. Okay, and also we need to note the fact that collector base junction is reverse biased, so there will be some kind of leakage current present. Okay, so collector base junction is reverse bias, hence there is some leakage current. So obvious question is, what do I exactly mean by the leakage current? Okay, so if it's a PNP, or let's say an NPN transistor, and it's an N-type semiconductor, it will have some kind of holes, right? Some holes will be here. Okay, that will be the minority charge carrier. Okay, and that minority charge carrier will actually correspond to a current which actually flows in the opposite direction. Okay, and since it does that, it actually corresponds to the leakage current. Okay, so that's very important. So you know that some of the current will actually not add up to it. Okay, so you have to just look into the circuit and start understanding that what exactly is leakage current. Okay, and you do understand that there will be some kind of leakage current, or I can write down because of minority charge carriers. Minority charge carriers. So you know it all depends on the basic thing, that how does the current flow from which direction to which direction it's flowing, and so on. Okay, so this is important. So it means that the collector current will actually consist of the emitter current. Okay, so hence the collector current will consist of the emitter current. Okay, so let's say I'm write down this. The collector current will be whatever actually we had as the emitter current. Okay, so that basically nothing but the current amplification factor. You can actually consider alpha into IE. IE. This is actually the current that will be there in the emitter part. So this is very near to 1, but practically you know it is 0.9 to 0.99. I'm saying is 5% and 95%, may not necessarily be. It might be a bit more or it might be a bit less. So it will actually vary between these values. Okay, so there is some leakage current. Okay, because of which you are not actually having that entire electron reaching the other end and actually completing the circuit. Okay, so that is being cancelled out. So you know if the emitter current is 1 and you multiply it with 0.9, let's say that the collector current will be 0.9 into 1, so it will be 0.9. Okay, so if I just take an example here, if we probably just write down an example here, it might be 0.9 into, let's say, 1 milliamperes maybe. So I can just say the collector current will be 0.9 milliampere. Okay, so this remaining 0.1 milliampere actually will be lost in the form of leakage current. So this is important. Okay. So we have this, okay, and this is again important. And then if I just want to find out an expression for this, I think this is also not very complicated. Okay, I'll just probably try to derive this expression. I think this is important. So we are just going to derive the expression for current. Okay, so let me just use the pen. I think it is very difficult to keep on typing everything. The total collector current. Okay, collector current IC, okay, is equal to whatever current you get from the emitter, okay, plus the leakage current. So I'll just write down the leakage current as ILEAK for now. In the next step, I probably will just write it down as IL. Okay. So you know IE is equal to 0. If IE is equal to 0, it means that the collector current cannot be 0, because there will be some leakage current which will still flow through it. Okay. Why do I say this? Because what happens is, if I is 0, that means this is open circuited. You don't have anything here. Okay. If the I is 0, that means this is open circuit. But then this circuit is still there. Okay, and then there is some current still flowing because of the minority charge carriers. Okay, so this is important. See, because if it is a this is n type, if this is n type, so this is n, let's say, it will have proton or the hole, sorry, or the holes as the minority charge carrier, and that minority charge carrier will flow because this is negative here. This is reverse bias, remember, this is negative here. So that minority charge carrier, that means the holes will actually start flowing. So that is actually constituting a part of the collector current, which is actually not because of the electrons that cross from the emitter to the collector. Okay, let me just repeat this. If I connect this in forward bias, I have the electrons going from the emitter to the collector. Okay, or maybe I can just take the other diagram. I think this is more easy. If we actually have this connection complete, we have the electrons flowing from the emitter to the collector. Okay, but if this circuit is not connected and this circuit is actually working, we have the minority charge carrier. If it is an n-type semiconductor, we have the minority charge carrier as holes here. Now this is actually connected in reverse bias configuration. So that means if it is an n-type, I'm connecting the positive terminals here. So I have the positive terminals here. So what happens is the holes will start flowing. Those are minority charge carrier. It does not constitute a very large current, might be only 0.1 or 0.05% of the total current. Okay, so that means even if there is no emitter current, there is still some collector current possible which flows through it. Okay, if we apply the reverse bias, and this is something which we call as the leakage current. Okay, so there are a lot of things which you can write, but I think it's a waste of time, because if you understand it, you can actually always make your own sentences and write it down. Okay, so uh, we also know something else. Okay, we also know that so in general what happens is, if IE is equal to 0, okay, IC will be equal to I leakage. Okay, let me write it down just as L. This can also be written in some books. Actually, the book that I follow, Mehta, okay, it basically writes them as ICBO. Okay, so what does this CBO actually stands for? Okay, collector base current with emitter open. Okay, so this basically stands for, just write it in short, collector base current with emitter open. So O stands for open. Okay, emitter open, and that is why it is collector base and open. So I hope you understand this, because if we actually don't have any emitter current, that means the input circuit is neither forward nor reverse bias. It is actually open circuit. Still you will have some current, and that is why we're writing down this as ICBO. Okay, so this is important. Also, we know, we have seen in the previous slide, that IE, emitter current, is actually nothing but base current plus collector current. Okay, so if we just mark this equation as number 1, we can actually do some replacements here. Okay, so what we can do is, we can just simply write it down as IC is equal to alpha into IB plus IC, okay, plus I, let me write it down as CBO. I think it's the same, or you can write down I leak also, doesn't matter. Okay, so if we just do the maths here, okay, you see this is a alpha and this is IC here, so I can take this IC on one side. Okay, so I can just take IC on one side, and the common would be nothing but 1 minus alpha. Okay, this is important, and is equal to alpha into IB plus ICB. Okay, so what is our aim? Our aim is to find out what is the collector current. So from here you get your collector current as, okay, alpha divided by 1 minus alpha into IB, okay, plus 1 by 1 minus alpha into ICB. Okay, so this is the expression for collector current. So you have to please remember this. Okay, I think this is important. Okay, so let's say I'll just write it down, this, remember. If you're doing any kind of numerical problem, probably we'll use this to actually find out what is the collector current here. So if you basically consider any kind of transistor here, you basically have got these. So you might ask me that is ICBO important? So some questions you'd see that they have not even mentioned anything as leakage current. So you can simply ignore this because this value is going to be very less. Okay, but then if they specifically mention that there is some leakage current, okay, you will definitely have to mention it. Okay, this ICBO is actually temperature dependent. Okay, it's basically temperature dependent. So if we have a circuit where actually people are talking about how high the temperature is, this ICBO will actually come into the picture. So if there is a circuit which is there at room temperature, okay, so what happens is sometimes that the thermal electrons, the thermal charge carriers are also taking part, okay. So it is also temperature dependent. So if you are considering something at room temperature, the number of minority charge carriers that will actually flow in the circuit will be much lesser in number. But if there is some temperature also involved there, apart from, let's say it's not 25 degrees centigrade, it's let's say around 70 or 80 degrees centigrade, adding to that flow of charge because of the voltage, there will also be some charges because of the temperature, as a result of which this will actually be having some significant value. But if it is room temperature, most of the time we say that we actually don't really need this. Okay, so this is a simple idea here. Okay, so probably I'll just finish the class with one question here, one numerical question. Okay, so probably all of you can do this, okay, after you just look into the formula. Okay, so let me just consider in a common base config, okay, or in a common base connection. Okay, current amplification factor, just ignore the typo if there is any. Okay, just listen to what I'm saying. Current amplification factor is 0.9. Now these kind of questions are actually quite common in even in a net exam also. Okay, so if the emitter current is 1, let's say, sorry, is 1 milliampere. Usually they will give you these kind of ranges because this is the amount of current that is getting generated. Okay, so determine the value of base current. So determine value of, so current amplification factor is given, emitter current is given, you have to just find out what is the base current here. Okay, you are not going to find out the collector current, please remember this. So collector current, you can straight away say that IC is equal to alpha into IE. Okay, then you can find out what is the collector current, and then you can use the formula of emitter current is collector current plus base current and find out the answer. Okay, so I'm not going to answer this, I think this is too trivial, very simple. Okay, the answer that you should approximately get is 0.1 milliampere. Please do it, practice. Okay, it's important. Maybe I can just give you another example here. Okay, and in number 2, in common base configuration, common base config. Okay, the IE, by IE I mean emitter current. Okay, is 1 milliampere. Okay, that's given if the emitter circuit, okay, is open. So that means we are slowly moving towards that dark current or the leakage current that we're talking about. The collector current is 50 microamperes. Okay, so I'll just write down U, but just consider it as micro. Okay, I don't have that scientific notation with this app. Find the total collector current. Total collector current. Okay, given alpha is equal to 0.92. Okay, 0.92. So what happens is this question actually explains a lot of things. Okay, whatever we have studied in theory, look into this. We are saying that the collector current is 50 microamperes if the emitter circuit is closed. This was 1 milliampere, so it is 10 to the power minus 3 order, but this is micro, that means 10 to the power minus 6. So it is 1000 order different compared to whatever you have from the emitter. So that means this current is very low. Okay, so if you are having a current of 1, this will actually contribute to 1.000, and then after that some value. Okay, so technically it's actually a very low value, and that is why when we do any kind of examples, okay, sometimes even if the leakage current is not mentioned, the answer will be very close to the actual result that you might get in the circuit. But then here it is specifically mentioned that the collector current is 50 microampere. So you really can't ignore this. Okay, so this is again important. So I think answer I can just write it down. So the answer to this is 0.97 milliamperes. Okay, so what I'd like all of you to actually do these two sums on your own. I think this will actually help you out. Okay,